Okay, so the next topic we're going to cover is satellite motion. Satellite motion is going to combine a lot of the different things that we've covered so far, so it's going to seem like a lot of review today. So for today's plan, we're going to do a quick reminder about Kepler's third law. We're going to introduce satellite motion. This is going to combine the earlier ideas of centripetal force as well as gravitational force. Then we'll look at a bunch of examples of satellite motion, and then of course we'll get some practice. So you do not need to write the slide down, so there's no reason to pause. We're going to talk again about Kepler's third law, which we covered last class. So last class we learned that a number is called Kepler's constant, which is K, exists for any object that has things orbiting around it. This constant is unique to that individual object. So all things orbiting that object will have the same constant. So it doesn't matter if you're talking about Earth going around the sun, or Mars going around the sun, or Jupiter going around the sun. If you took their orbital period and squared it, the orbital period here, and you squared it, and you divided it by the orbital radius cubed, that's going to equal the same number, k, no matter what object you're looking at orbiting around that central object. So again, if it was the orbital period of Earth going around the sun divided by, the orbital period of Earth squared divided by the orbital radius of Earth cubed, that number that it's going to spit out, k, this right here, is going to be the same as if you took the orbital period of Jupiter squared divided by the orbital radius of Jupiter cubed. So for any objects orbiting around the same central focus, so for instance for any of the planets orbiting around the sun, if you took their orbital period squared and divided it by their orbital radius cubed, it's going to equal the same number. And that number we refer to as the Kepler's constant for that focus. So this formula is not on your formula sheet. Just remember T again is the period, or in other words, how long one complete orbit takes, and R is the average orbital radius. And we like saying average here. It's not just semantics. It does have a purpose. The average orbital radius is given because orbits actually aren't perfect circles. They're ellipses, or in other words, ovals, right? So there's times where it's closer to that focus than other times. We just talk about R being the average orbital radius. So the units when you use this don't necessarily need to be in seconds and meters as long as you're consistent. So if you had orbital period, for instance, in days, you would just have to make sure if you're comparing it to anything else, you make sure you use that orbital period also in days. Okay, so we're going to see an example of this. I do want you to jot this down, so just pause here. All right, Ganymede is Jupiter's largest moon and the largest moon in the entire solar system. It's even larger than the planet Mercury. It takes 7.15 days for Ganymede to orbit around Jupiter. It orbits at an average distance of 1.07 times 10 to the 6 kilometers. What is Kepler's constant for Jupiter? Now, of course, we're saying the Kepler's constant for Jupiter because Ganymede is orbiting around Jupiter. That means Jupiter is our focus. And the Kepler's constant will be the same for any focus, right? So we can maybe use this to compare it to another moon of Jupiter, for instance. Anyway, so Kepler's constant, as we had from that formula, is K equals T squared over R cubed. Now the nice thing is your units don't actually matter here. It doesn't matter what units you use as long as we're being consistent. And because this question says nothing about what we want the units for Kepler's constant to be, we have total freedom over what we put in here. We just got to make sure we're putting in an orbital period squared. Well, an orbital period is how long it takes it to go around once. The question tells us it's 7.15 days. So we'll say it's 7.15 squared divided by our orbital radius cubed, which it was also given to us, except in kilometers. But again, that doesn't matter. We can use whatever we wish. So it'd be 1.07 times 10 to the 6, all cubed. Throwing this in your calculator is going to give you K equals, and we need to round to our nearest 3 sig digs, 4.17 times 10 to the negative 17. 10 to the negative 17. Now, before we close this off and put a box around it and say it's our final answer here, it is important to list the units. Again, the units don't matter for what you put in, but when you give your answer, you should state what units it's in. Since we put days on our numerator up here and kilometers in our denominator up here, and then we squared the numerator and we cubed the denominator, we can say that the units on this would be days squared over kilometers cubed. Then we can put a box around this and say that that's our final answer for this question. So this next question builds off that first one. I'll give you a second to jot this down. Another moon of Jupiter is Io. It orbits Jupiter at a closer distance of 4.22 times 10 to the 5 kilometers. How long does Io take to orbit Jupiter in days? So you might remember from that last question, we found Kepler's constant K to be equal to 4.17 times 10 to the negative 17 days squared over kilometers cubed. This number is going to be the same for anything that's orbiting around Jupiter. So even though we used Ganymede in the last question to figure out this Kepler's constant, we can now use this same number for Io. So we can say that this unit, this K, equals the orbital period of Io, which is what we're looking for, so T squared, over the orbital radius of Io cubed. Now, the orbital radius of Io was given to us in kilometers, which matches the units we had for our Kepler's constant. So we can just put in our denominator here, 4.22 times 10 to the 5, and then that whole thing cubed. To get T all by itself, first we need to times by 4.22 times 10 to the 5 all cubed on both sides. This is going to give me 3.1362 equals T squared. And then, of course, we want to square root both sides so we can get T completely on its own. And I'll say that's T equals to 3 sig digs, as the question asks, 1.77. But let's ask ourselves real quick. T is our orbital period. Since the Kepler's constant that we calculated in the last part of this question was given in days squared per kilometers cubed, the units on this T are going to have to be days. So 1.77 days is the orbital period of Io. And what's really cool about this, I think I mentioned this last class as well, this is accurate. This actually works. If you know some data, you can use it to extrapolate for anything else that's orbiting around that same object. So our new topic for today is going to be satellite motion. So just pause here so you can write this down. All right, so I want you to first look at this picture that I have in the bottom right. We have a satellite that's going around Earth. It's orbiting around Earth. What I want you to note is that for any object orbiting around another, there's actually two forces at play. There's the centripetal force that we've been talking about this entire time, this whole unit. We call that Fc. Fc always points to the center of a circular motion. But also, as we'd be more familiar from earlier, especially in our dynamics unit, we also have Fg pointed in the exact same way. In space, those would be the only two units that are actually, the only two forces that would ever actually be acting on this, because in space, the vacuum of space is more or less a frictionless environment. Since those are the only two forces acting here, and they're both pointing in the same direction, we can therefore say that our centripetal force is equal to our gravitational force. Now in space, we had a very fancy formula for force of gravity. It was capital G, which is the universal gravitational constant, or 6.67 times 10 to the negative 11, times by the mass of one object, times by the mass of another object, all divided by the radius between those objects squared. For force centripetal, we had two different formulas we had. We had the one that said mass times velocity squared divided by r, and then we had the other one that said mass times 4 pi squared r over t squared. So we had two different formulas that we'd have to use for force centripetal. Now, depending on what a satellite motion question is asking you, you're going to use one of these two different formulas to find the remaining information. So for example, if I asked you to find how fast that satellite was going, the only one of these two formulas that has a velocity in it is this one, right here. If I was asking you for the orbital period, in other words, how long it takes the satellite to make one complete orbit around that object, you'd be using this formula because it contains the orbital period. Now, something else I want to point out with these formulas is something very bizarre that we haven't actually dealt with yet. I want you to first notice the left-hand side of both of these equations. I actually listed a little bit more information in this. I listed the mass as being mass 1 to match it with mass 1 on the right-hand side of the equation. The mass in a centripetal force formula is the mass of the object that's doing the orbiting. In other words, the satellite that's going around the object. So the mass 1 that I've listed in both these formulas, so right here and right here, is actually the mass of the satellite, not the mass of the planet or the other thing that's causing the gravity, right? Now, the reason that this is important is you're going to notice that that mass 1 appears on both sides of the equation. And on both sides of the equation, it's showing up in the numerator. There's a really interesting trick that can help us out here to simplify our formula down. In reality, since we have mass 1 on both sides of the formulas, on both of these formulas, on both sides of the equations, I should say, and on the numerators for both of them, if you imagine you could divide both sides of each of these equations by mass 1, that would cancel mass 1 out here and cancel mass 1 out there. In other words, the equation just becomes v squared over r equals gm2 over r squared. Likewise, you could do the same with the second formula. Mass 1 on the top, mass 1 on the top. If you just divided both sides by mass 1, they're going to disappear. Now, furthermore, with this very first equation, there's something else you can actually do. There's something else we can cancel out on both sides of the equation. Notice we have a radius that shows up on the denominator on both sides of the equation. If we multiplied by r on both sides, that would get rid of the r here. And since this one on the right-hand side is an r squared, it would kind of knock it down from being an r squared to just an r. So an r to the power of 1. In other words, this equation 1, just to rewrite it, could be written as v squared equals gm2 over r. So it becomes a little bit simpler rather than the bulky formula that we started with in the first place. Now with equation 2, if you look at your r's, the r on the left side of the equation is on the numerator, and the r on the right side of the equation is on the denominator. There's not a heck of a lot you can do to rearrange this, but if you want, you could multiply by r squared on both sides to get rid of it on the right side, but then that's just going to combine with the r on the left side to turn it from an r to the power 1 to an r to the power of 3 inside those brackets there. So this one could be rewritten as, notice we got rid of our m1, we could write this as 4 pi squared r cubed over t squared equals gm2. And that's about as much cleaning up we can do with that formula. So in other words, what I'm trying to say on this slide, I know it was kind of a lot of information to absorb. Oftentimes these questions don't actually give you enough variables to throw in for every single one of these variables. So for instance, oftentimes I won't even give you the mass of the satellite. You're just going to have to recognize that algebraically in these two formulas, they're going to cancel out. Fundamentally, the most important thing to understand here is that your FC equals FG. From there, you can just apply the two different formulas that we have for FC and figure out what you're looking for and cross out what you already have as a duplicate on both sides. Okay, so we're actually going to see it in action now. I want you to jot this question down into your notes. So the center of Earth's moon is 3.844 times 10 to the 5 kilometers away from the center of Earth. Determine the orbital speed of the moon. Now, this isn't the same as those, Keplers Constant questions where your units don't matter. With these, because we're using our force centripetal and force gravity formulas, we need to make sure we're using our common base units here. In other words, this kilometer unit isn't going to work for us. Before we even begin, let's make sure we change this, this radius into meters. To change it into meters, we just need to times by 1,000. This is actually going to turn it into 3.844 times 10 to the 8 meters. Now that I have that cleaned up, let's recognize we're looking for the orbital speed of the moon. The moon is orbiting around the Earth. That tells us a relation that we have is that our centripetal force is equal to our gravitational force. Now our centripetal force has two different formulas we could use. Because we're looking for our orbital speed, we're going to use the force centripetal formula that contains speed. In other words, mass 1, that's the mass of your satellite, or in this case the moon, the mass of the moon times by velocity squared over r. There we go. This is going to equal our gravitational force formula, and we always, for space, use that really bulky one, capital G, m1, m2 over r squared. Like I mentioned on the last slide, we can start canceling things out, and we actually have no other choice here. The only thing we were given was r. That was the only piece of information that was given to us. Now, in this formula, of course, the FG formula right here, m1 is going to represent the mass of the moon, and m2 is going to represent the mass of the Earth. Well, the mass of the Earth is actually given to you on your formula sheet, so that actually is something we know. Just like capital G being the universal gravitational constant, that's also given on your formula sheet. But mass 1 was not given to us. We don't know what the mass of the moon is, and it's not in your formula sheet. So we have no choice but to use a little bit of fancy algebra here and notice that since m1 is on the numerator of both of these expressions, we can just cancel them both out. Also, while we're at it, just to make our life a little easier, since r is on the bottom of both of these expressions, it's here and it's here, we can times by r on both sides to cancel it out here and knock this down from an r squared to just an r. Cleaning this up is going to give us v squared equals the universal gravitational constant times the mass of Earth divided by the radius. We're looking for the orbital speed. We have everything else here. Let's throw those numbers in. V squared equals capital G, which again on your formula sheet is given as 6.67 times 10 to the negative 11, times m2, which is the mass of the Earth. The mass of the Earth is given on your formula sheet as being 5.97 times 10 to the 23, or 24, sorry, 24. Said 23, but I meant 24. Divide this whole thing by r, which we calculated at the top up here, to be 3.844 times 10 to the 8 meters. I'll throw this in my calculator really quick. That's v squared is going to equal, and I'm going to keep pretty much as much of the numbers as possible, 10358 97.5. And then, of course, to find the speed, or v, just square root both sides. So v is going to equal, and we'll round it to the nearest 4 sig digs, 1,018 meters per second. And we know the units are meters per second here because we use standard units for everything else. G is a really complicated mess of units. You can take a look at your formula sheet to see exactly what this is. M2 is in kilograms. R we made sure was in meters. All of these units are going to cancel out using some data analysis here. I don't know. You know what I mean. Unit analysis. There it is. Holy smokes. You can tell I'm getting tired. Unit analysis is what I'm talking about here. Using unit analysis, you can figure out that it is going to be meters per second. Okay. Bottom line is, just to make this simpler, as long as you're using common units, your answers are going to come out in common units as well, right? The unit analysis, so analyzing what the units of each and every single individual piece that you threw in there would actually be able to tell you that this will be meters per second. All right, we'll do another example here. Just stop and pause just so you can write this down. Landsat is a satellite that takes pictures of Earth's ozone layer and geological features. It orbits at an altitude of 912 kilometers above Earth's surface. What is the orbital speed of the satellite? So a couple of things before I start this question. First of all, you're going to notice it's asking for the orbital speed. 1 second, there you go, orbital speed. And it gives us an altitude. Let me just remind you that an altitude is not the distance between the center of the Earth and this satellite. The altitude is just the distance from the satellite to the surface of the Earth. So in other words, that piece right there is going to be the 912. When we are looking for orbital speed, whenever we use r for radius, it actually talks about the distance to the center of the object it's orbiting. So in other words, we're actually going to have to take this 912 kilometers and add it to the radius of the Earth. And just remember, the radius of the Earth is actually on your formula sheet. It is 6.37 times 10 to the 6 meters. Now, since that was in meters, we should also make sure that our 912 kilometers is also in meters. Well, to turn kilometers into meters, you just times by 1,000. So we're going to add 912,000 meters. This is going to give us a total radius here of 7,282,000. Now, remember again, if we're looking for the orbital speed of the satellite, because this is a satellite, we can say that FC equals FG. And we had two different formulas for FC, and since we're looking for orbital speed, we're going to use the one that, of course, contains speed. So again, we'll say it's mv squared over r equals g m1 m2 over r squared. And again, this mass in the force centripetal formula on the left here would actually be mass 1, namely the mass of the satellite itself. Now we'll do that trick I showed you just a second ago as well. Since we have an m1 on the top on both sides of this equation, we can actually just knock both of them out. And since we have an r on the left side of the equation on the bottom, we can take one of the r's on the right side of the equation down. So we'll just drop it from an r squared down to an r. What this will leave us is it'll leave us with v squared equals g m2 over r. And since we're looking for orbital speed, we just have to plug in all this other information. Now, v is what's unknown. Capital G is actually the universal gravitational constant that's on your formula sheet. And m2, in this case, it's not the mass of the satellite, it would actually be the mass of the Earth, which is on your formula sheet. R, of course, is something we calculated at the beginning of this question, so really we just have to throw all of our numbers in here now. This is going to become v squared equals g, which again on your formula sheet is 6.67 times 10 to the negative 11, times by mass 2, which again is the mass of the Earth, that is 5.97 times 10 to the 24. And then we're going to divide that by the radius, which we found at the beginning of this question to be 7,282,000. Throwing this in my calculator is going to give me v squared equals, let's see here, 54,682,642. Now, of course, this isn't our final speed. We need to take the square root of this now. If we square root both sides, we're going to get v equals to, I guess the nearest 3 sig digs would be 7.39 times 10 to the 3 meters per second. So again, the key to this question was to recognize that with satellite motion, we know that the centripetal force equals the gravitational force. And then we could do some tricks with some algebra here, noticing that we had an m1 on the top on the left side and an m1 on the top on the right side, so they could cancel out. And we could also just make our life easier a little bit by cutting out the r on the bottom of the left side of the equation and one of the r's on the bottom of the right side of the equation as well. All right, so this next part of the question isn't going to be looking for the orbital speed, it's rather going to be looking for the orbital period. Now, before I begin this question, again, since it's the exact same altitude that we had in the last question, I'm just going to copy the exact same r from the last question as well. That was 7,282,000, and that was in meters, of course. So in this question, we're looking for the period of the satellite. Now, the period of the satellite can still be found. It's just going to be found using a different version of the FC formula. We still have FC equals FG, but instead of using the FC formula that contained V, we're going to use the one that actually contains T instead. So the other formula is going to be M1 times 4 pi squared R all over T squared. And again, period, which is the amount of time it takes to complete one orbit, that's capital T. So that's what we're looking for here. This is still going to be equal to g m1 m2 over r squared. That's the force of gravity formula. Now, the exact same thing happens in this setup as it did in the last one, where we have an m1 on the top of both equations. That means we can cross it out, and that's really good because, of course, again, we don't actually know what the satellite's mass is, and m1 would represent the satellite's mass. So the fact that that can cancel out on both sides really makes our life a lot easier here. There's something else we can do to make our life a little easier here. We can't cancel our r's out because we have an r on the top over here and r is on the bottom over here. But what we can do is if we times both sides of the equation by r squared, that'll cancel it out on this right side, and timesing by r squared on this left side is actually going to tack it on to the other r that was already there. So again, what this is going to end up looking, or how this is going to end up looking, I should say, is going to be 4 pi squared r cubed over t squared equals gm2. And then since we're looking for t, it might be a good idea to get that t squared all by itself. And to do that, we just need to times both sides by t squared. So that would remove it on the left side and tack it on to the right side. And then we can divide away by gm2. So really our formula is going to look like 4 pi squared r cubed over gm2, and that equals t squared. So from here, we can just throw the numbers in. We know what our R was. It's the same as it was in that last question. Pi, of course, is just a constant number. We know the value of pi. Same with capital G. We know the value of that. And M2, just like in the last question, is just the mass of the Earth, which is found on your formula sheet. So from here, we can take all this information and throw it in. So it's 4 pi squared R, which is 7,282,000. And we have to cube that, all divided by G, which is 6.67 times 10 to the negative 11, times by the mass of the Earth, which is 5.97 times 10 to the 24. 24, there you go. Now again, both of those numbers that I just put on the bottom of the denominator there, both of those are actually on your formula sheet, so you can always look those up. Now, I'll throw this entire left-hand side of my equation into my calculator, and when I do that, I need to be very careful that I put the numerator in its own full set of brackets, and then divided by the denominator in its own set of brackets. That's just because I like throwing this in the calculator all at once. Like I like doing this in just one big step. If you're not comfortable with that, you can break this down and do it in smaller chunks, but whatever floats your boat. Anyway, what I've got for this left side of the equation now, I suppose would be 38,283,496 equals t squared. And then, of course, I just need to square root both sides because I want to get t all by itself. And if I square root both sides, I get to 3 sig digs 6.19 times 10 to the 3, and that would be seconds, equals t. Now, you might be wondering, how did I know that that was seconds? Well, we know it's seconds because we used all of our common base units in this whole question. When I threw in, for instance, our R value, I made sure that that piece up here was in meters. This piece right here is a whole jumbled mess of units. If you look in your formula sheet, it actually gives it to you, so you don't need to worry about that. But mass 2, of course, on your formula sheet is clearly listed as being in kilograms. As long as you're listing your base units and using consistent base units like kilograms or meters or seconds, etc., your answer is also going to come out in base units. But again, you can just use unit analysis to figure that out if you need. Unit analysis will tell you exactly what your units that are going to appear in your answer, of course. Okay, to close things off, I'm just going to end with some key hints. So just pause this slide and you're going to want to jot this down. Okay, so to go about these kinds of questions, I want you to think about what the question is asking you to find. If it's asking for, let's say, a period, you know you're going to have to use that formula that has the period in it. Or if it's asking you for a velocity or a speed, you're going to have to use that formula that contains speed in it. So basically, you just have to look through all of your formulas and find the formula or formulas that provide you with what you're looking for. You also need to recognize, of course, the relations between the forces in your examples. With these satellite motion questions that we've just done, the relation, of course, is always Fc equals Fg. And a free body diagram almost always helps. If you have some object and then something else orbiting around it, going in a constant direction around this object, there really is only going to be two forces involved. If it's in this orbit by gravity, you know there's gravity pushing it towards the central object. And since it's moving in circular motion, you also know that there's a centripetal force. And because those are the only two forces available, you can tell that centripetal force and the force of gravity are going to be the same because centripetal force actually acts almost like a net force. Now, I also want you to remember that frequency is not in any of our formulas. Frequency is directly related to the period. If you find the period, then you can also find the frequency. The period and the frequency are just reciprocals of one another. So in other words, if you knew, for instance, that the period, so the amount of time it takes for something to make one full orbit was, let's say, something silly like 5 seconds, then the frequency, which tells you how many orbits it makes per second, the frequency would be 1/5, just the reciprocal of that. Now, frequency isn't measured in 1/seconds, like technically I suppose it would be, but there's actually another unit we use for that. 1/seconds is actually hertz, just a capital H and a Z, right? Those are the units we use for frequency, so if it's ever asking you for frequency, that really means just find the period first and then realize that frequency is 1 over your period. So for practice, I want you to complete the satellites worksheet. I also want to make sure that you've completed all of the previous handouts. So it's not enough just to have tried a couple questions here and there. You need to have completed the entire handout, or all the entire handouts that I've given so far. Now the quiz, which is on Tuesday next week, is going to contain 5 multiple choice questions, 3 numeric response, and 3 written response questions. And it's going to cover everything that we've done so far in this chapter. That's going to include circular motion, so centripetal velocity, acceleration, and force. It's going to include vertical circular motion problems. Those are the roller coaster type problems and the bucket of water type problems, where basically you just had to remember that if something's being spun around in a circle, your tensional force or your normal force, if it's a roller coaster kind of question, I'll just say Ft, your tensional force, is going to actually be minimized, there you go, minimized at the top, and your force of tension is actually going to be maximized at the bottom, right? Also with those kinds of questions, a free body diagram always helps. Your centripetal force is always pointing towards the center of your vertical motion. And you also would, of course, have the force of gravity always pointing straight down. And then your tensional force, or your normal force, if it's a roller coaster question, is always pointing towards the center, just like your force centripetal. Now, another thing you're going to need to know is banked curves. And remember, we do not give you the formula for it. It's tan theta equals v squared over r times g. You do need to remember that formula. It's not going to be given to you. Then, of course, another thing you're going to need to remember is the Keplers laws. There were 3 of Kepler's laws that you needed to remember. But the most important one of Kepler's laws that you need to remember is Kepler's third law, which says that there exists a Kepler's constant, which we called K, for any object that causes an orbit. And that Kepler's constant for that object will be the time period squared divided by the radius cubed of any of the objects that are orbiting around it. Now, it doesn't matter what object orbiting around it you choose, as long as you're squaring the period and cubing the orbital radius, it's going to give you the Kepler's constant for that object. And of course, you can also further this by saying if you looked at the period of object A squared divided by the, oops, I drew a B there, that should be an A, divided by the radius of that object A cubed, that's going to be equal to the period of another object, we'll call it object B squared, divided by the radius of object B cubed, right? So you can sort of use this as like a ratio to help you solve other parts of problems using this relation. Then, of course, the last thing you need to know for the quiz is satellite motion, as we covered today. That's just where FC equals FG, right? And it's up to you to determine which FC formula to use, because there are 2 different ones that you have to use depending on what the question is asking for. So I would pause this right here. I'd leave this up on the board for the rest of class. As always, use each other as a resource. Make sure you're understanding all this material, and if you need any help, please ask.